It's clear that some problems are difficult and some problems are easy. And what we've just seen is that even seemingly natural problems, like how do I compress something optimally, is a problem in this case that's so hard it's actually impossible. So what we're going to do now is wrap up our discussion of algorithms and complexity by talking about the space of problems that lie between impossible and possible. So we know that some problems are fundamentally harder than others. And I'm going to tell you some things that we know about the runtime of optimal algorithms for some problems. So we've just discussed, but have not proven, but I have the links to the proof if you'd like, that the Kolmogorov complexity of a bit stream, calculating that is impossible. Just does not exist. That's as hard as it gets. Lower down the list, well, we might consider, given an array, does it contain two items, such that f of x1, comma x2 is equal to 0 for some arbitrary function, any arbitrary function. This algorithm naturally is just going to be n squared. We have to test all the pairs. There's no shortcuts we could do because in this case, f is a black box. There's the three-sum problem, which is a little easier than this problem, which says, given an array of numbers, are there any three numbers that add up to 0? And this, well, there's an algorithm that's n squared divided by log n divided by log n to the 2/3. So this is just slightly faster than n squared, and so it's a little better than this one. Comparison-based sorting, we did a proof and showed that that's n log n, the best possible algorithm. And finally, finding the median of array is n time. And all of these are assuming we're using some simple model of computation where we're using pairwise comparisons for decisions. Okay, so that's a hierarchy here. These are some easier problems, and we grow in difficulty till we get up to this point. As a quick aside, nobody's actually proven a lower bound on 3-sum. That's interesting, at least. But it's widely conjectured to be slightly less than n squared. So the thought is you can't do much better than n squared. In fact, until 2 years ago, it was widely believed you could never do better than n squared till this algorithm was invented, but you can see this isn't much of an improvement. Okay? So let's explore the space in between here, and I'm going to kick it off by bringing up a problem called the independent set problem. So what is an independent set? Well, given a graph, an independent set is a set of vertices, here, let's say the red set of vertices, in which no two of the vertices in that set are adjacent. So if you look here, I have 24 dots, or vertices, and 9 of them are red. And if you look at each of these red dots, none of them is touching another red dot. So in that case, this is an independent set. So in other words, given a graph, color some of the dots red such that none of the red dots are touching. That's the independent set problem. And so the independent set for some particular k says, for a given graph, does there exist an independent set of size k? So in this graph, does there exist an independent set of size 9? Yes, here it is. Does there exist an independent set of size 24? No, because we'd have to color all the vertices red, and obviously the vertices would be touching. Okay, so question for you. What I'd like you to do is come up with an algorithm for solving independent set. Don't worry about runtime. Just come up with something that works and have at it, and I'll chill out here. But a key point is that your algorithm has to work for any graph and any k. All right, I have a graph here that might help you think, but might just make things more confusing. Okay, so I'm going to brute force it. That's my hand. So my brute force algorithm is just going to try every coloring of any number of red dots and see if any of them works. So how many possible colorings are there? Well, there's 2 to the n, right? So for every vertex, we can either consider it white or red. And therefore, if we have n such vertices, there's 2 to the n possible combinations, kind of like binary numbers. Because if you have an n-bit binary number, there are 2 to the n different numbers. Okay, so after I pick a particular coloring, I iterate over these colorings somehow. I'll check if the number of colored vertices is equal to k, right? So if I color in only 2 of them red, because that's one of the colorings, but I'm actually supposed to be doing the problem k equals 5, then that will rule that particular coloring out. So first I check if the number of colored vertices is correct. That takes n time because we're going through all the vertices, counting out the reds. And if that works, then we'll say for every red vertex, well, we'll check that all the neighbors are white of that vertex. So for each red vertex of which there are k, it can have up to n neighbors, and so the runtime of this step should be kn. Now if both of these checks succeed, if we find a coloring such that there are k red ones, and every red vertex has only white neighbors, then we're done and we return true. However, if either of the checks fails, then we'll go on to the next coloring. So the runtime for this algorithm in the worst case is we have to go through all the vertices. So that would be for all 2 to the n colorings, we have to do k times n work right here, and also n, but this is bigger. And so the runtime will be k times n times 2 to the n. And of course, k can be no larger than n. So we can just say this is n squared times 2 to the n. That is the runtime of our algorithm. So it's exponential times a quadratic, but basically just exponential, really slow, okay? But it works. This algorithm will work. So now the question is, how hard is this problem fundamentally? So let's suppose we have an algorithm TUISA, which is the ultimate independent set algorithm. That's what that stands for. It's the asymptotically optimal algorithm for the independent set problem. So what can we say about the worst case runtime of TUISA, much like we did with comparison sorting? Well, we know it's at least n, right? I mean, without even thinking, because we have to do something with at least every vertex. So we can say it's lower bounded by n, the worst case runtime of this algorithm. And certainly it's no worse than the algorithm we just derived, which is n squared times 2 to the n. And so the question is, can we say more? Just like we did with comparison sorting, can we somehow inch this up? And so in order to say more, we're going to have to take a couple of detours into reductions and into complexity classes. So that's the setup. We want to know how hard or how ultimately difficult the independent set problem, which gives us a bound on TUISA.